damped harmonic oscillator. It's a problem that comes up in a lot of classes, physics classes. It's a problem that can be applied in different situations. It's not just for springs, but let's get a solution for the damped harmonic oscillator. So this is just a normal harmonic, simple harmonic oscillator, or normal. You could call it normal, right? And you know, I'm going to assume that you know how to solve this. If not, let me know. I think I have a video on that, but I'll be happy to remake that. And I'm actually remaking this video because I didn't like my old one. So let's imagine that I have a mass on a spring in one dimension, no friction. Well, yeah, there's a little bit of friction, but and there's the position of the mass is x, and there's a force that depends on the position of the mass, negative kx, where k is a spring constant. Now suppose that it's moving. Let's say it's moving this way with the velocity x dot. Remember, x dot is dx dt. We use this dot notation. I haven't seen that before. That's what that means. So that's the velocity. Then there's also a force due to this motion pushing in the opposite direction, negative b x dot. So I have the following. F net in the x direction is going to be the spring force, negative kx minus b x dot, and that's going to be equal to mass times acceleration, which is mx double dot. So that's the equation that we want to solve. And how are we going to solve that? Okay, so let's just go ahead and write this. I'm gonna just do some manipulations here. So let's write this as solving for x double dot. So I'm gonna actually, let's get x double dot by itself. So I'm going to divide both sides by the mass and then move everything to the same side. So this gives me x double dot plus, I'm going to put the next term, b over m x dot plus k over m x equals 0. So that's the form of the equation that we want to solve. So all I did was just, divide by m and then move these terms to the other side. Now, b is a constant that depends on the situation, right? It's the drag constant. K is the spring constant. M is the mass. Those are all just constants. So let's replace these constants with other constants. If you remember the simple harmonic oscillator, K over M is the angular frequency squared. So let's use that. So I'm going to say omega naught squared is K over M. That's my undamped angular frequency K over M. And for this B over M, let's say B over M is equal to 2 beta. Or beta is just another parameter, so we don't have to write a fraction. And this is where you'd say, why is there a 2 there? Why not just call it beta? And you could just call this beta, but it turns out to make things a little bit simpler later on if we call that 2, and you'll see later on. So those are my two substitutions. With that, I get this, x double dot plus 2 beta x dot plus omega naught squared x equals 0. And so it's still just a differential equation, but it's a little bit different differential equation because the constants are different. Okay, now let's do another substitution. I have x double dot, the second derivative. I have x dot, the first derivative, and I have x. So we can kind of make this look like a quadratic equation if I say I'm going to define the operator d as the derivative with respect to time. And then d squared is the second derivative with respect to time. So I can write this as d squared x plus 2 beta dx plus omega naught squared x equals 0. And I can then factor out the x, right? And so I get this. D squared plus 2 beta d plus omega naught squared x equals 0. And if you think this all looks weird, you're right, okay? Differential equation, just a bunch of little tricks that we use to solve things. So, but now let's take this equation right here. So let's write it back up here. I have d squared plus 2 beta d plus omega naught squared x is 0. That's what I want to solve. And this is an operator, right? Because those are derivatives. Now, either this operator is 0 or x is 0. I don't want this situation where x is equal to 0 because that's just boring. It's true, it would work, right? If I say x is a function of t is equal to 0 and I plug back into this equation, this differential equation, it works. 0, 0, 0 equals 0, but boring. So instead we want this to be 0. And you can see this looks like a quadratic equation, and if that's true, I should be able to factor this. So you can actually write this as d minus r1 times d minus r2 x equals 0, where r1 and r2 are constants because 2, beta, and omega naught squared are just constants. So I should be able to factor that. So how do you factor an equation like this where I'm treating d as a variable? Well, the answer is use the quadratic equation. Yes, from 8th grade. It comes back. So remember, if I have a x squared plus b x plus c equals 0, then x is going to be negative b plus or minus the square root of b squared minus 4ac, all of that over 2a. So here, a is equal to 1, b is 2 beta, c is omega naught squared. So I'm going to get the following solutions. R1 will be the plus, R2 will be the minus. So let's do the plus. R1 is going to be equal to negative b, so that's this, negative 2 beta, plus the square root of b squared. So that's going to be 2 beta squared, which is 4 beta squared, minus 4. And I was looking for 4 up here. There's no 4 because this is a number. A is 1, C is omega naught squared, minus 4 omega naught squared. All of that divided by 2a, but a is just 1, so that's 2. And then R2 is just going to be the exact same thing, negative 2 beta minus, right, it's a minus the square root of 4. This marker, can I do a quick pit stop? My marker's dying. Minus 4, that one's better, beta squared minus 4 omega naught squared, all of that over 2. Now right up here, I can factor out a 4, and the square root of 4 is 2. And then I have a 2 and a 2, so all of these cancel. Isn't that nice? Oh, not the omega, that one. So I get R1 is negative beta plus the square root of beta squared minus omega naught squared. R2 is negative beta minus the square root of beta squared minus omega naught squared. Now do you see why back over here we did that? If you didn't do this, back over here, I would just get beta squared. Let's say I said b over m is beta. I'd get beta squared minus 4 omega naught squared. That 4 is there from the quadratic equation, and it wouldn't cancel. You'd still get the solution. You just couldn't. It'd still be as a fraction, and that's fine. You'd still with the same thing. It's just that this looks prettier. That's all. That's it. Okay, so I know R1 and R2. I know these values, but I still don't know the x. So let's just take this right here. So this says this operated on x is equal to 0. That's one option. So if I say d minus R1 operated on x is 0. Now let's switch this back to our actual notation. So this is the first derivative, and that's just a constant. So this says x dot, that's the derivative of that, minus R1x equals 0. And I can solve this for x dot. X dot equals R1x. And now I need to solve that differential equation. Well, that's not too hard, right? This says, what do I take the derivative of? And I get a constant times that function x. Well, if you took differential equations, you know that that answer is an exponential. So I can say x as a function of t is equal to some constant c1 e to the r1t. If I take the derivative of that, I get an r1 out front with the original function, so it satisfies that. And then I can do the same thing for d minus r2x and equals 0. And that gives me, doing the same thing, I'd get x dot equals r2x. So I get x as a function of t is another constant c2 e to the r2t. And if both of those are solutions, then the sum of them should also be a solution. So let's just write the sum of those two as a solution. And we need two constants, and that's one of the things. We need two constants because we have two initial conditions, the initial position and the initial velocity. So now we have this. X as a function of t is, focus, pull it down a little bit, c1 e to the r1t plus c2 e to the r2t. And then I can put in my values for c1 and r1 and r2, and r1 was the plus. Okay. So I get x as a function of t is c1 e to the negative beta plus the square root of beta squared minus omega naught squared, all of that times t, because that's r1, plus c2 e to the negative beta minus the square root of beta squared minus omega naught squared, all of that times t. And I have an exponential here, right? So if I have an exponential of a sum, e to the negative beta plus this, I can write that as e to the negative beta t times e to the square root of beta squared minus omega naught squared t. And I can do the same thing over here. So I can factor out this e to the negative beta t and write this as e to the negative beta t times c1 e to the square root of beta squared minus omega naught squared times t plus c2 e to the negative square root of beta squared minus omega naught squared t. And you can see that it really does help over here, going back to the beginning, that, right? Because now I can write this exponential as not a fraction, and it just makes everyone happy, right? And part of solving the damped harmonic oscillator is making people happy. So I'm happy. Are you happy? We should be happy. Okay. But this is the solution, right? But the behavior of the solution depends on a couple of things. Let's first check the value of beta, right? Beta is important here. So let's say that, and omega, beta compared to omega naught squared. So let's first say that beta is equal to 0. If beta is equal to 0, and remember, this is going to be equal to b over 2m, right? So if beta is b over 2m. So that means that, well, the drag coefficient b is 0. So there's no drag, right? And if I put in beta is equal to 0 up here, this term is just 1, right? E to the negative 0 is 1. So then I get over here, I get a 0. And so I get negative omega naught squared t, negative omega naught squared. And so this negative omega naught squared is going to be I omega, right? The square root of negative omega naught squared is just going to be I omega naught. So I can write this, if b is equal to 0, x as a function of t is 1, right? That's that. Then I have c1 e to the I omega naught squared plus c2 e to the minus I omega naught squared t, omega naught t. And this is sines and cosines, right? So if you go back to your solution for the harmonic oscillator, that's the same thing, right? That is a harmonic oscillator. That's one of the solutions. You could write it this way. You could write it as a sine omega t plus b sine omega t, cosine omega t, or you could write this as a cosine omega t plus phi. Either whatever you want to do. But this is one of those solutions. That is a simple harmonic oscillator. And that's good, right? Because this is a simple harmonic oscillator. Okay, now let's look at the case where beta is greater than omega naught squared. Beta greater than omega naught squared. So going back over to our solution here, if beta is greater than omega naught squared, then this is just some number, right? That's just a number. And then that's a number. And I forgot how to show that these both decay. I'm not completely prepared, I guess. Let's see. Overdamped. beta is equal to, let's see. Oh, that's right. Okay. So let's bring this negative beta back in over here. And I get x as a function of t is c1 e to the negative beta plus the square root of beta squared minus omega naught squared t plus c2 e to the negative beta, that's all parentheses right there, negative beta minus the square root of beta squared minus omega naught squared t. Okay, so that's a positive number, that's a positive number. We can actually write this as pulling this negative sign out front. I'm going to make that plus, I'm going to make that negative and say negative. I'm going to pull this one out front, and that's negative plus. But the important thing is that this, if beta is greater than omega naught, this is still an exponentially decaying term. That's an exponentially decaying term. I'm going to plot this in a little bit, but that's one of the solutions. I'm going to go ahead and say, this is called overdamped. And no one cares about that. That's fine. The next one is called critically damped. Beta is equal to omega naught squared, in which case it's a little confusing, and I don't want to get into solution of this because no one ever gets into the solution of this. I can model this quite easily, but in general, you're going to get a weird solution. It looks something like x as a function of t is a plus b t e to the negative beta t, I think. But anyway, that's the solution. It's going to look something like that, and there's other t's in there because you need two coefficients, and that's all I'm going to say about that. I apologize. But here's the one that we won't really want. What if beta is less than omega naught squared? This is critical. This is called underdamped. Underdamped. And in this case, let's go back up here to our previous solution. The problem is that if beta squared, beta naught squared is less than omega naught squared, then when I take this difference under the square root, I'm going to get a negative number. When I take the square root of a negative number, I'm going to get an imaginary number, right? So let's make the substitution. Let me write down. I'm going to put this on a new piece of paper. So here's my solution in my generic solution. Paper's not straight. Okay, straight paper. You got to have straight paper. X as a function of t is e to the negative beta t times c1 e to the square root of beta squared minus omega naught squared t. That's right? Yeah. Plus c2 e to the negative square root of beta squared minus omega naught squared t. So let's say omega is equal to, let's say omega is the square root of omega naught squared minus beta squared. So it's a positive number. If I switch this direction, right, if I flip the order and beta squared is less than that, then this is going to be a positive number. But that means that the square root of beta squared minus omega naught squared is going to be equal to, that's going to be the opposite. And if I switch that, I get negative I omega. Is it negative I omega or omega, I omega? I think it's negative I omega. No, it's just I omega. And omega is this, right? It's not omega naught. Omega naught is the undamped frequency. This is the damped frequency. They're different. So if I plug that in up here, I get this. X as a function of t is e to the negative beta t times c1 e to the I omega t plus c2 e to the minus I omega t. That's pretty cool, huh? Okay, now let's go ahead, and this is a simple harmonic oscillator. We've seen that before, and this is an exponential amplitude term, right? So we should get this simple harmonic oscillation with a different frequency, omega, not omega naught, and it exponentially decays. What if you want to find C1 and C2? Okay, so let's say that x at 0 is equal to x0. So if I put in t equals 0, I get 1, and then for that, and then I have C1 times e to the 0, which is 1, so C1, plus C2. So x0 is the sum of C1 and C2. What about x dot? X dot as a function of t. I can take the derivative of this. It's a little bit more complicated, but let's do it anyway. I'm going to take the derivative of this term, so I get negative beta e to the negative beta t times C1 e to the I omega t plus C2 e to the minus I omega t. Then I have to take the derivative of this term times that. So let's say plus e to the negative beta t times the derivative of this is going to be equal to I omega C1 e to the I omega t plus minus I omega C2 e to the minus I omega t. Now if I put in t equals 0, so x dot of 0 would be equal to, this is going to be 1, so I get negative beta. This is 1, C1 plus C2, that's 1, so plus is 1. And this is going to be 1, 1, so I get plus I omega C1 minus I omega C2. And you can see that it gets a little complicated here. If I set this equal to V0, that's fine. But if I set that equal to 0, then really what I'm going to do up here, it gets a little complicated. So let's just say C1 equals x0 over 2, C2 equals x0 over 2, and use that as our solution. And I'll go into the initial conditions a little bit later, but that should work. Okay, so we're done, except that we're not. Because now you know what I do. You know, if you've seen this channel before, if you know anything about me, and maybe you don't know much about me, hello, my name's Rhett, how are you doing? You know I like to solve things numerically too. So let's do a numerical solution. And let's go back to the original equation. Focus. Okay. So here's what I had. I had x double dot equals negative b over m x dot plus minus k over m x. Right? That was the ma equals the drag force, the spring force. Well, let's break this into small time intervals. Delta t equals 0.001 seconds. During that time interval, I can calculate x double dot using this equation. And now if I assume it's constant, I can also write x double dot is equal to delta x dot delta t. So instead of writing x double dot as a derivative, I'm going to use a difference. And let's say that the thing is moving. I can write this as x2 dot minus x1 dot over delta t. Here, x1 dot is the velocity at the beginning of the time interval, x2 is at the end. So if I multiply by delta t and add x1, I get x2 dot equals x1 dot plus x double dot delta t. That's important. This is important. Now I can assume x2 dot is constant. x2 dot is going to be delta x delta t, or x2 minus x1 over delta t, and that's a t. And so this gives me x2 equals x1 plus x2 dot delta t. Now this is x2 dot because I just updated the velocity, so it's not the velocity at the beginning. I'm using the velocity at the end. This order of operations does indeed matter. But that's it, right? Now I know that both the position and the velocity after the time interval, after that short time interval. If I want to do the next time interval, I just use my new value of x, my new value of x dot, and I go up here, find my new value of x double dot, and repeat the whole thing. So if I wanted to do 1 second, I would have to do this 1,000 times because I have a time step of 1/1000th. No one wants to do that, so we're going to do it in Python. But we do need numerical values. We need numbers to do this. Okay. So let's switch over to Python and let's do this. Okay, I'm in Python right here. I'm going to give you the code. And, you know, I'm using WebVPython. If you haven't seen what I'm doing before, I like to use WebVPython. And I like to do things in the simplest way, not the most elegant way, but the way that's easiest to understand. So that's what we're going to do. And we're going to make a graph. So I'm going to go ahead and make a graph. G1 equals graph. X title equals time. Y title equals X. And let's give it a width of 400, height of 200. Now I need a graph. So let's call this FU, because it's going to be the underdamped. I'm going to start with the underdamped. FU is G curve, color equals color.blue. Now I need my parameters, so I need my mass. I'm just picking some values, 0.1. I need, okay, K. K, let's say, is 1. That's fine. Now, instead of picking B, I'm actually going to calculate omega naught and then omega naught squared and use that to calculate beta and then use beta to calculate B. That way I know if it's underdamped, overdamped, or whatever, right? So instead of like guessing around with the parameters. So let's say omega 0 is equal to the square root of K over M. And now I want it underdamped. So I'm going to say beta equals 0.5 times omega naught. So it's going to be underdamped. And now I can use that to calculate B. So B is equal to, let's see, what was it? Beta is B over 2M. So it's going to be 2 times M times beta. Is that right? B is 2 beta M. Yep, got it. Okay, cool. Now, the other parameter, I need my initial conditions. So let's say X is 0.01, X dot is 0. I'm going to start it from rest. T equals 0, dt equals 0.01. I usually have this a little bit bigger. That's better. Okay. Now let's do a 3-second loop. So while t is less than 3, the first thing I'm going to do is to calculate x double dot. X dd dot, I'm going to call it x double dot. It's just going to be my differential equation. Negative b times x dot divided by m minus k times x over m. Now I'm going to use that to update my x dot. X dot equals x dot plus x double dot times dt. So again, this is a make equal to sign here. So we don't need the indices. This is going to take the value of x dot and then calculate this and then make that the value of x dot. So we don't have to worry about all those indices. And then x equals x plus x dot times dt. And then I need to update time. T equals t plus dt. Now I'm going to plot it. Fu dot plot t, and x. If this works, I'm going to be pretty impressed with myself because, you know, I'm just doing it on the fly. Okay, I did it. So it looks good. We can always test, right? Let's just test if this is working. I'm going to let b equal 0, and then it should be a harmonic oscillator. So let's just multiply this by 0. Okay, that looks good. Let's go ahead and make beta a little bit smaller. Let's make this 0.2 to be less, more underdamped. That's a little too much. Oh, it's times 0. I got the 0 over here. That looks pretty good. Let's let this run for a little bit longer. Maybe increase the spring constant. So let's say 2. I want to get more oscillations in there. Okay. Let's make this 3. Okay, that's pretty good. So you see here we have an oscillation that's damped and decreasing exponentially. I'm going to go ahead and plot this just so you can see. I'm going to plot that e to the negative beta term times initial position just so we can see that. You see this in the books all the time. So let's make another one. F exp equals G curve color equals color dot red. And then I'm going to plot that down here. F exp dot plot t. And then this is going to be equal to 0.01 times the exponent of negative beta times t. I think that'll work. Boom. There's your exponential decay on the top. You can put one on the bottom too, but there's your exponential decay along with the thing. So that's pretty cool. Happy with that. Okay, let's plot. I'm not going to make these separate graphs. Let's just do it, right? Let's just plot. I did zero damped. I did under damped. Let's do over damped. So I'm going to get rid of this curve because I don't want to, it's going to be weird. Get rid of that curve. Let's do over damped. All I have to do is say beta is greater than omega. So let's say this is 1.2 times that and plot it. Right? I don't have to worry about changing all these other expressions because I'm not plotting the theoretical. I'm numerically calculating it. You could and you should, as a homework, go do it yourself. Take this code, which I'll give to you, and then plot also the theoretical calculation and see if they agree. They agree, trust me, I've done it. Okay, so here's your over damped. You see it doesn't oscillate, it just dies down over there. And then finally we can do critically damped. So critically damped, I should do these together, but let's just try it. I'm going to change this to 1 and run it. And it looks mostly the same, so let's do both of those. Let's do that twice, right? So here's critically damped, and let's call this FC for critical and FO for overdamped. But that means I'm going to either need to run the whole code twice or put 2 X's in there. I'm going to run the whole code twice because I don't really care. Okay, so here's my beta equals 1. This is critical damped. I've already got that, right? But I do need to change this to FC because I've changed it right there. Now I'm going to copy all of this right there. And I'm going to go down here. And this is like, oh, don't do that. That's rude. You can't disrespect the computer. Oh, I can. Okay, so beta, B. I need up here beta too. I'm not going to change omega. So beta, let's make it overdamped. I'm going to make this 1.2 like I had before. And then everything's the same. I reset my x value, reset my x dot, reset time. I just need to change this to critical. Wait, what do I have up here? Oh, the overdamped. It should be overdamped. Sorry. Okay, let's run that. Okay, see, they look very similar, but the numbers are very similar too. But they are indeed different. This one's the overdamped, and that's critical damped. And let's just change this overdamped to even more overdamped. Let's say 1.8. I'm just picking numbers here. I'm going to run it. And there you go. That's critical versus overdamped. Okay, there you go. Hope you had fun. I had a lot of fun. Made it to the end. You should give yourself a thumbs up or something like that. Maybe a double high five, if that's what it takes. I mean, this is a hard problem, okay? But as long as you have an equation of that same form, so this comes up in LRC circuits, this comes up in, I can't remember where else, but it comes up. It does. It comes up. So there you go. Code down below. If you have any questions, let me know, and I'll see you guys later.